Come hang out and chill with me. I'll teach you enough math to get a math degree.
Hi everyone, so just a quick intro. In this video, I'm going to start talking about linear algebra, and what's different is I'm actually going to be teaching someone. So my good friend and wonderful human being, Brian, has offered to let me teach him linear algebra, and that's what you'll be observing today. So we're going for a very chill feel on this one, but we're also trying to be comprehensive. So over the course of these videos, you'll pretty much learn everything you would learn at a comprehensive introductory linear algebra course. You know, no matter what fancy college you go to, we're gonna hit it all. But we're gonna go through it fairly slowly, so if you're in a little bit of a rush, maybe this is not the right one for you. But overall, hope you enjoy. Another thing, the video is very thoroughly time-stamped at the bottom, so if you're just interested in one particular thing, or if you need a quick refresher on an idea, just check out the timestamps at the bottom. Just to get warmed up, let's start by just solving a simple linear equation, the likes of which maybe you've solved many times in your life. So let's say you have x1 plus x2 is 1, and 2x1 minus x2 is also equal to 1. How might you solve this particular equation?
Well, the first thing I'd want to do is I'd want to solve for either x1 or x2 in the first equation given.
Okay.
You can get that x1 would equal 1 minus x sub 2.
Okay, perfect. So x1 equals, I'm just going to write down what you're saying, 1 minus x2. All right.
Exactly. And then we can actually substitute what we've just evaluated into the second equation.
Correct.
So we can multiply all of that by 2.
Very good. So,
yeah.
2 times 1 minus x2.
Yep, exactly.
Minus x2 is equal to 1. And let's expand. So you get 2 minus 2x2 minus x2 is equal to 1. So 2 minus, in fact, 3x2 is equal to 1, right? Which gives me that negative 3x2 is equal to negative 1. x2 is equal to a third.
Yep. And
what would that make x1?
So then what we'd want to do is we can plug in x2 to either of these equations. So that would make x1 2/3.
x1 would be 2/3. Correct. Now, the method you used, substitution, is not the only way to solve an equation like this. Well, good job, by the way. That's good.
Thank you.
But you can also, and in fact, this turns out to be a slightly easier way to deal with things. You can add and subtract multiples of one equation to the other equation.
And would you want to do that to make it easier to simplify the entire equation?
It turns out to be a great way to eliminate variables, and it's actually a fantastic starting point for linear algebra. So for example, notice that if you were to add the first equation to the second equation, it would eliminate the x2 variable. What would you get if you added the first equation to the second equation?
So as you said, the x sub 2's will cancel, and then you'll have an x sub 1 plus 2x sub 1. So you'll have 3x sub 1 equals 2. 3x
sub 1 equals 2, and that gives you x sub 1 equals 2/3. Substituting into the first equation, you get that x sub 2 equals 1/3. Fantastic. You'd agree, a faster way to do things.
Much faster, depending.
Okay, excellent. One thing we can always do with equations is we can add multiples of one equation to another equation. And that will never change the solutions of the equations. So for example, if I start with this system of equations, and instead of the second equation, I replace it with the first equation plus the second equation. So I've turned this system into a new system now. x1 plus x2 equals 1. And then the other equation is now 3x1 is equal to 2. I think you'll agree that that's what we did, right? So it's not like we lost the first equation. In fact, we needed it to finish the problem, right? But what we did is we replaced the second equation with the sum of the first and the second equation. And now, does that make sense?
Yeah.
Okay, perfect. And so you see, this system and this system, they have the same content, right? They have the same solutions.
That's very interesting. Yeah.
But this system, the second one, is easier to deal with than the first one.
Yeah,
right?
because we've eliminated the x sub 2 in it.
Very good. This is an entry point into something called row reduction.
Oh, very interesting.
Okay. Row reduction is the idea of, by the way, some people call this Gaussian elimination for historical reasons as well, but it's the same thing. It's fine. It doesn't matter.
Yeah,
it doesn't matter what you call it. Row reduction is a list of legal moves you can do to a system of equations that does not change the answer to those equations.
It just manipulates them.
It just manipulates them. And the idea is, hopefully you are doing these manipulations to get a simpler set of equations. You're not going to want to manipulate your equations to make them more complicated, right?
Yeah, exactly.
You're hopefully going to want to manipulate your equations in an effort to make them easier to deal with, okay? So there's two notions, in fact, there are three notions that we have to make abundantly clear in this situation. Number one, what are the moves that are allowed? What are the things we are allowed to do to equations in an effort to make them easier? Make sense? So that's the first question. What are the moves? The set of moves that are allowed is called row reduction.
Okay.
Question number two, what does easier look like, right? What does it mean? Like, what are we driving towards? What is our kind of like goal state? What is our end state? How do we know we're moving in the right direction, right? Because sometimes linear equations can involve, a lot of equations, a lot of unknowns. It's nice to have a destination point. Okay? That is encapsulated in these things called echelon forms. Okay. So just to keep in mind the structure, row reduction is the moves we are interested in. Okay?
Yes.
Echelon forms are sort of the end states we're interested in. How they tell us the direction of travel. They tell us what we want our equations to look more and more like in an effort to make them easier and understand their behavior.
So just to clarify, when you say echelon forms, do you mean, for lack of a better explanation, the final product of your row reduction?
Exactly. Okay. What the idea of row reduction is to reduce your system of equations to be in an echelon form.
Okay. Yeah.
Okay.
So far I'm with.
The idea is that presumably, if you have it in echelon form, you can just read off what your answer is real fast.
Yeah.
That's the idea. The other thing to look for, and the other thing I want to go over in this lesson is, what are the possibilities here? So sometimes linear equations have solutions. Sometimes they don't have solutions. Sometimes they have infinitely many solutions, right? And what are the possibilities here? And how do you know which situation you are in? Okay. These are the things we are going to be going over.
Awesome.
So far, so good?
Yeah, perfect.
Okay. What are the allowed moves? What is row reduction? Well, there are three allowed moves. You can add any multiple of an equation to any other equation.
Okay. So that would be the same as what we
just
do in algebra. We just don't think about it.
Yeah. But you will see why systematizing all this stuff is a very good idea. Okay. Because by the end of this, we'll actually be able to prove that the possibilities I'll lay out for what can happen really are the only possibilities. And you'll be able to see them instantaneously because we're studying it in such a systematic way. Okay.
I'm excited.
Okay, excellent. So, first possible move you can do with row reduction is you can add any multiple of an equation to another equation.
Yeah.
Okay? So add any multiple, right, of an equation to another. Okay. Move number two. You can multiply any equation by a non-zero number. Okay. You can also multiply any equation by a non-zero number. Okay. Okay. Number three, you can switch the order of the equations. Right? If you have four equations, 1, 2, 3, 4, you can swap like 2 and 4, and it's not a problem. So you can switch the order. Okay, and it turns out this is sufficient. You know, these three moves are row reduction. Okay.
Yeah.
All right. Let's actually use this procedure in an effort to solve a system of linear equations. By the way, any questions about these?
No, so far I'm good.
Okay. Let me write a system down. Okay. So, how about this one? Let's make it complicated. Let's actually use a 3-variable system with 3 equations, just so you can see that this is like having this organization is actually useful. Because
yeah, for sure.
the first time I studied row reduction, I actually thought it was pointless. Because, you know, I've been solving systems of linear equations my whole life, you know, and so it's just like, why are you teaching me a different way to do something I already know how to do? So I think it's good to start with a more complicated example so you can see that these organizational methods are worth learning. Okay?
Yeah.
Let's start this way. So x1 minus 2x2, I'm just copying this down, plus x3 equals 0. That's the first equation. The second equation is like 2x2 minus 8x3 is equal to 8. Okay, and then 10x1 minus 10x3 is equal to 20.
All right, awesome.
Okay. This is the system we are going to attempt to solve. I'm just going to move this over a little bit. Okay. So, first things first, you will notice when you are solving a system of equations, it is annoying and painful to write x1, x2, x3 over and over and over again. So what we are going to do, first move, is we're just going to stop writing them. We're going to convert this system of equations to what's called an augmented matrix.
Okay.
It's the same information, literally the exact same information, but we will not write x1, x2, x3. Okay?
So instead, are we just going to put the coefficients of them?
We are just going to put the coefficients. Exactly. So 1, -2, 1, 0. 0, because the coefficient of x1 in the second equation is 0, right?
Yeah.
2, -8, 8. And then 10, 0, -10, 20. I'm going to put a little line here to signify where the equal signs are. And by the way, a little preview. These shenanigans will actually allow us to solve like multiple systems at the same time as well. So this bar is somewhat ominous in that, or maybe not ominous, but a harbinger of good things, because you could put multiple coefficients on the other side and actually solve it all simultaneously, which you would not be able to do, right? Traditionally. Okay, let's get this started. And as we do this, I will also try to give you an instinct for the kind of shape we are going for. Okay, we are shooting for a staircase type shape. Okay. This is the sort of shape we are gunning for.
Okay.
Under the staircase should be zeros, but I'll talk in more detail about it. Okay.
So then would the 2 in index row 2 and index 2, and then the -10 and row 3 index 3 be the ones we want to turn to zeros?
Those two. Wait. Say those again.
The 2 in the middle row we'd want to turn to 0 then.
No. So I was actually thinking more like this type of staircase. So under the staircase is zeros.
Okay.
You'll see what I mean.
Yeah. I see what you're saying.
For sure, no matter how you slice it, this 10's got to go.
Yeah.
Okay. It is.
Yeah, for sure.
What I'm gonna do is subtract 10 times row 1 from row 3.
Mm-hmm.
Okay, let's do it.
And that's because there's a 1 in the first row's index.
Exactly. So I'm going to use that 1 to kind of annihilate the 10.
Okay.
Okay. So I have 1, -2, 1, 0, 0, 2, -8. 8. These are the same. I didn't do anything.
Yeah. We're only modifying the third row.
We are only modifying the third row. So far. 0, -2 times -10 is 20, right? So
Yes.
this becomes a 20.
Oh, I see. So since we're changing the third row, but from the first row.
Yes.
Okay.
You can. It's just like adding it's just like subtracting 10 times the first equation from the third equation, right?
Yeah.
And you have to do it like all the way through, right?
Yeah.
Okay, perfect. So, and then this becomes a -20.
-20. Yeah. Okay. Perfect. All right.
Perfect.
I'm with you.
And so this just stays 20, right?
Yeah.
0.
Because it's a 0.
Okay, perfect. Okay, this is looking pretty good. What I'm going to do is I'm going to multiply. I'm going to multiply the third row by 1/20, or in other words, divide by 20 in the third row. Okay, so I'm just gonna.
Okay, and is that just because you want ones there?
Well, I just noticed they were all divisible by 20, and yeah, you'll see. So you notice that we were able to use this one to annihilate things we didn't like.
Yeah.
Right.
Yeah.
So actually, having ones is nice for that reason.
Yeah, I see what you're saying.
Okay, so having ones here is going to be very nice for us. In fact, while I'm at it, I am going to also multiply the second row by a half, because why not?
Is that because we want that middle 2 to become a 1?
Yeah, so I noticed they're all divisible by 2, right? So why not, right?
Okay.
So now I have 1, -2, 1, 0, 0, 1, -4, 4, right? 0, 1, -1, 1.
Yeah. Okay.
How's it looking?
Good.
All right, excellent. So now, actually, what would you like to do?
Well, I was gonna say, if we're gonna keep going for that staircase shape, then we're gonna need to get rid of the 1 on the bottom row.
Okay, very good. How would you do that?
Couldn't we multiply it by 2 since there's a -2 at the top?
Multiplied by 2 since there's a -2 at the top. The issue is, I think the next move you were going to do is add like the first row to the bottom, but notice that would bring the 1 back down here. You see that?
Yeah.
Okay.
Yeah.
What else? You pointed out that it might be a good idea to target this 1 down here, right?
Mm-hmm.
Just to get that sweet staircase shape. And so you can do that. So what would you have to do in order to do that?
Well, since we have a 1 in the middle row and the corresponding index, I think you'd call it, or spot, we could just subtract row 2 from row 3.
That's correct.
Yes.
And what would you get if you did that? I'll write it down here.
You would get the same numbers for the first row,
Yes.
same numbers for the second row,
Very good.
and it would be 0, 0, and then -4 minus -1, which is -3. Yes.
So, wait. -1 plus 4, right? So 3 and -3, right?
Yes. 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 Okay. I
No-
get it.
No worries. And while I'm at it, I'm just gonna multiply this by 1/3, just so we get the 1.
Yeah. Just so yeah. And so just to clarify, the reason we're doing this is because now in the final row, if we were to turn this back into an equation, we would only have 1 variable, and so we automatically know the third unknown.
You are 100% correct, and a little bit ahead of me. And so yeah, what is the third variable?
So then, wouldn't x3 just equal -1?
You've done it. Very good. X3
very
is
helpful.
indeed -1. And actually, you can stop right here. You can what's called back substitute your way to victory. So once you know what x3 is, what does the second equation say right now?
Yeah, because now that we know x3, we can instantly solve for x2.
And once we know x2 and x3, we can instantly solve for x1. By the way,
really convenient.
I'm so happy you got that. Very good. This process we've just described is called back substitution. Okay.
You're saying the process is in when you resubstitute
Yeah, you
our modified matrix.
you have like a bottomish variable, and then you update
plug it.
Yeah, you plug it in the equations up top. That process is called back substitution. Substitution. Okay, excellent. Also, I want to point out to you another thing. This matrix, as it stands, this one right here, is in echelon form. Okay?
Okay.
I will be more technical and more precise in explaining exactly what echelon form is.
Okay. That was my next question.
But I just want to point out that we sort of naturally got to this destination, or maybe some people might say not so naturally, because like I may have forced your hand a little bit by mentioning the staircase to start with.
Yeah, but for sure.
Hey, you see the use of the staircase, I hope. It's
enormously helpful.
Enormously helpful indeed.
Yeah, at least in my experience in some of my science classes, some of these systems get really, really complicated to solve for.
Right. However, I want to show you that you can take this a little bit further. You don't have to back substitute right here. In fact, you can take care of the work of back substitution without ever getting out of an augmented matrix. You can keep the matrix augmented and do a couple more row operations in order to do the work of back substitution and solve for all the variables. Okay?
Okay.
Let's do that. So I'm just gonna tidy up the board. Now, let's do a couple more row operations in order to clear out all the unnecessary variables from the remaining equations. So, as an example, what I can do is I can add 4 times row 3 to row 2, and I can also subtract row 3 from row 1. And what that will do is it'll have the effect of eliminating this, let me change colors. It'll eliminate this -4 and this 1 and turn them both into zeros.
I think I see what you're saying, but I'll definitely have to follow along with your work a bit here.
Okay, let's try it out. Let's do those 2 operations that I just mentioned and let me know what you will get.
Okay. Well, so for the first operation, if we're subtracting, if it's R1, row 1 minus row 3, then it would be 1 minus 0, which is 1.
Mm-hmm.
-2 minus 0, which is -2.
Very good.
I see. And 1 minus 1, which is 0.
Very good.
Okay.
Don't forget to finish at the very end.
Oh, yes. And then it would be 0 minus -1, which is 1.
Very good.
Okay.
Excellent. And for the second one?
We are adding 4 rows of 3. So the first spot would still stay 0 because there's just 0.
Good.
Second spot would also be just 1 still because it's 1 plus 4 times 0.
Very good.
And it would be -4 plus 4 times 1, which is 0.
Excellent.
And then you would get 4 plus 4 times -1, which is 0.
Excellent. And then we didn't do anything to the last row. Yes.
Nice.
Intuitively, what might you do next to get this to be as pristine as you could possibly make it? If you read the third equation, what does it tell you?
That 10x sub 1. Are you saying the third equation of the original? Or
No. The newly minted equations after row reducing so much.
Well, tell us that x3 is equal to -1.
Correct. What does the second equation tell you?
That x2 is equal to 0.
Very good.
Yeah.
Now, the first equation you can't read off quite as quickly because of this niggling -2, right?
Yeah.
So maybe let's get rid of it. Okay.
Oh, we want to simplify to 1, so we immediately have an evaluation for the corresponding variable.
Exactly.
Okay. I see.
So what would you do to this matrix?
Wouldn't we want to multiply it by -½ or half? I don't know which one you'd want to pick.
But that would ruin this one up front, right?
I see.
Yeah.
Couldn't we add row 2 since the other 2 spots are zeros?
Yeah, so what multiple of row 2 would we add to row 1?
Well, we'd be adding the 1.
Right. But how much times row 2 would be adding to row 1?
I'm sorry, I'm a little confused by your question.
So you're saying we need to add row 2 to row 1, and you are correct about that.
Okay.
But if we just added row 2 to row 1, it would turn this -2 into a -1, right? But I would rather turn it into a 0, right?
Oh, so we can add row 2 times 2.
Excellent. That's exactly what we have to do.
Okay, I see.
So do this, and now we get this, which is, think about where we started, and this system of equations is very easy to.
Yeah, and I was gonna say, now we have ones only in the x sub 1 spot for row 1, 1 in the x sub 2 spot for row 2, and x sub 3 is in the 1 spot.
Excellent.
For row 3. Yeah, okay.
So in fact, what's the answer? Let's lay it on me. So x1 equals.
x1 is 1.
x1 is 1.
x2 is 0, and x3 would be -1.
Brilliant. Perfect. We are done. Okay. This is.
Quick question.
Yeah. Go for it.
So to me, this didn't necessarily seem much faster than back substitution.
Mm-hmm.
Is that not always the case when you go, say, into more sophisticated systems?
I'm going to hold off on that question.
Okay.
And proceed to another example. It is a very good question. I will answer it later. Basically, I guess I'll give you a preview. So there's two different styles you can go for when you row reduce a matrix.
Okay.
You can go for echelon form, which we already had when we were at that back substitution step.
Oh yeah, when we had the finalized matrix.
Yeah, when we had that matrix with that pretty staircase shape.
Yeah.
We were ready to back substitute right then and there. If we had only gone to that point, our matrix was in what's called echelon form. However, if you go all the way like we did here, this new matrix is in what's called reduced echelon form.
And is that because everything in their corresponding spots is a 1?
Yes.
Oh, okay.
And also notice above and below the ones are zeros.
Yeah,
right?
yeah.
Reduced echelon form is the simplest form you can have to read solutions off of.
Okay.
And this is getting a little bit ahead of ourselves, but a single system can have many echelon forms. So if you and I set out to row reduce a matrix, we might get different echelon forms, but it turns out there's only one reduced echelon form for a system.
Okay, I see what you're saying.
So that makes it very easy to check your answers. In fact, if you ask your computer right now to row reduce a system, it'll convert the system to reduced echelon form, which will make it easier for you to check your answer. Okay?
Okay, yeah, that makes a lot of sense.
Okay. Let's, before we continue, try another system. Okay? Now that you're getting the swing of things. Okay. All right. So let's try the following system. I have it written down over here. So it's x2 minus 4x3 equals 8. Then 2x1 minus 3x2 plus 2x3 equals 1. And 4x1 minus 8x2 plus 12x3 equals -14.
Okay.
All right. Have at it.
All right, so the first thing we're going to want to do is make this an augmented matrix.
Okay, very good. Let's do that real quick. So 0, right?
Yeah, then it'll be 1, -4, and 8.
8, very good.
And it'll be 2, -3, 2, and 1.
Mm-hmm.
Then it'll be 4, -8, 12, and -14.
Very good, yes. All right. What row operation would you like to do first in this situation?
Well,
assuming. Oh, go ahead.
I was gonna say, you said one of the rules is we can swap the rows.
Yes, exactly. And I see you're going for that staircase vibe again.
Yes,
right?
yes. I'm trying to get this 2 out of there.
Okay, good.
Middle row. So could we theoretically swap row 1 and row 3?
Yeah, why not? Let's do it.
Okay,
let's swap rows 1 and 3. I'll draw a little arrow here, just to indicate what we did, in case we need to check our work.
Yeah.
4, -8, 12.
Mm-hmm.
-14. Let's see. 2, -3, 2, 1.
Yeah.
And then 0, 1, -4, 8.
And 8. Yeah, perfect.
All right.
So, since I'm trying to get rid of this 2, couldn't we subtract half of row 1 from row 2?
Good. Let's do that. row 1 over 2, right?
Yeah.
Normally I avoid fractions because I'll be honest with you, row reduction is extremely error prone because you're doing like lots of tiny arithmetic operations, and the bigger the matrix, like the longer you're doing it, the more they add up. Basically, if you have a long enough row reduction, it's basically a certainty that you'll mess up at some point.
Yeah, I already I've garnered this feel.
So yeah, be extra cautious, especially when fractions pop up.
All right, sounds good.
Right. But 4, -8, 12.
Yeah, so the first row will stay the same.
The first row will indeed stay the same. What will happen to the second row?
So now what I'm going to do is I'm going to multiply each of these first numbers by half and then subtract them from the corresponding indexes of the second row.
Good.
So it would be 2 minus 4 over 2, so 2 minus 2 is 0, which is what we were going for.
Yes.
And it would be -3 minus -4. It's going to be 1.
Very good.
Yeah, and then it'll be 2 minus 12 over 2, so 2 minus 6, which is -4.
Very good.
And then it's going to be 1 minus 7.
1 minus 7.
Yes, so 8.
8.
Yeah.
Very good.
And then it's going to be just the same third row.
Okay. Now what would you like to do?
I have a feeling we need to make this 1 in the third row go to 0.
Okay, so you would subtract the second row from the third row, right?
Yes, exactly.
All right, let's see what happens when you do that. So the first row stays the same.
Yeah.
Okay. 4, -8, 12, -14, 0, 1, -4, 8.
Yeah.
Okay, what happens?
So then it's going to be 1, well, it's going to be 0 for the first one. It's going to be 1 minus 1. And then it's going to be -4 minus -4.
Which is?
0. Yeah, 0. 8 minus 8, which is 0.
Interesting. What happened to the third equation? What does it say now?
That x sub 3 is just 0.
Oh,
no, you can't because there's not even a coefficient.
There's not even, so what is it actually? It's just saying 0 equals 0.
Is that an error on our part?
No, it just says 0 equals 0 now.
Huh.
But let's, I'll guide you through the next steps, and then we'll talk more about it in a minute.
Sounds good.
I'm going to divide, this is very simple as it stands, but I would like to make it a little simpler instead of back substituting immediately, in line with what we did last time, right? So I'm just going to do a couple more row operations here.
Yeah, for sure.
Okay. So what I'm going to do is I'm going to divide the first row by 4, right? So I'm going to multiply it by 1 over 4. Okay.
Yeah, okay.
You do that, it becomes 1, -2, 3, and what's -14 over 4? Just a -7/2, right?
Yes, -7/2, yeah.
Okay, and this stays the same. 0, 1, -4, and 8.
Yeah.
0, 0, 0. I've run out of room. I'm just gonna move this up. I didn't mean to interrupt you, but what did you say?
Oh, all good. I was gonna ask, would we then want to make that -4 in the second row simplified, or do we just want to keep that as 0, 1, -4?
As I said, I like the way you're thinking, but I'm going to take the lead on these next couple of row operations, because there's a particular phenomenon I would like to point out to you, and then I'll talk through what is happening here. Maybe I'll put it over here. Done. Deselect. Okay. What I'm going to do actually is I'm going to get rid of this -2. Okay?
Okay.
I'm going to get rid of this -2. And I'm going to do that by adding twice the second row to the first row. Okay?
Okay.
1, 0, and
oh, okay.
And then 3 minus 8, right? So -5.
Yeah. Mm-hmm.
Right? And this one's a little trickier. -7/2 plus 16 is what?
32. 2 over 2 minus 7 over 2, which is 25 over 2.
Very
Yeah.
good.
Sounds right.
And 0, 1, negative 4, 8,
Mhm.
0, 0, 0. Okay?
Yeah.
Turns out this is the end of the line forms. This is as far as we can go. This matrix is in reduced echelon form for this system. Once again, I have not told you what reduced echelon form is, but I want you to get a feel for it before I dive into it. So this particular matrix is in reduced echelon form. You notice it has like a kind of staircase vibe to it.
Yeah.
What are the equations here, if you were to write them out? So what equations, what have become of the original equations? What are the equations now? So the last one is 0 equals 0, so that's a throwaway.
Yeah.
But what are the other two?
Wouldn't the first one be x sub 1 minus 5x sub 2 equals 25 over 2?
Minus 5x sub...
Up 3, x sub 3, my apologies. Equals 25 over 2.
Mm-hmm.
And then it would be x sub 2 minus 4x sub 3 equals 8.
Okay, these two equations, right?
Yeah. Mm-hmm.
Let me rewrite them another way. I can rewrite them as x sub 1 equals 25 over 2 plus 5x3.
Yeah.
And x2 equals 8 plus 4x sub 3, right?
Yeah, I see.
In our row reduction process, all the moves that we did were legal moves, right?
Okay.
So we did not lose any information going from this system to this system, right?
Yeah.
However, this system of 3 equations turned into a system of 2 equations.
Yeah.
Right. Another thing I want you to note, this variable, x3, is what we call a free variable.
Okay. And
the idea is, pick your favorite value for x3. It can be anything. You can set it to be 1. Yeah, sure. If you set it to be 1, that'll give you an x1 and x2 that work.
Okay.
You just plug in x3 equals 1. These equations give you an x1 and x2.
Yeah.
You can set it to be 0. And then x1 would have to be 25 over 2. x2 would have to be 8.
Oh, okay. Yeah. Mm-hmm.
So x3, no matter what choice you make for x3, you can find an x1 and an x2 that work with your choice of x3.
Oh. So in some way it's like creating many.
Yes. This system has infinitely many solutions. This is the second possibility that we're dealing with.
Oh, very interesting.
So the first system we dealt with had a unique solution, right? There was only one value of x1, x2, x3 that worked.
Yeah.
Right? This system, however, has infinitely many solutions because no matter what we set x3 to be, we can find a value of x1 and x2 to work with. Right?
Yeah.
Does that make sense?
Yeah, very interesting.
x3 is called the free variable in this situation. x1 and x2 are called the pivotal variables in this situation.
Okay. Yeah.
Okay.
Yeah, that makes sense.
You pinpoint the pivotal variables as follows. The pivotal variables have pivots in the columns when you're done row reducing. The pivots being like the pivots in the staircase.
Yeah, I see.
Okay. The free variable does not have a pivot in it when you're done row reducing.
Oh, okay. Yeah, I see what you're saying.
Okay. Whenever you have a free variable, whenever you're in a situation where you have a free variable, you'll notice not all of your columns will have pivots when you're done row reducing.
Okay.
And so, guess what? And this gets into why row reduction is so interesting and it gives you so many powers. You can now, before you even finish, you actually could have said right at this point that there were going to be infinitely many solutions. Because you could have read right from there. In fact, you could have even done it earlier, that there was not going to be a pivot in every column. In fact, the minute you got the zeros at the bottom, you knew there was not going to be a pivot in every column.
Oh, and if we're missing one of the 3 pivots in this case,
yes,
then we automatically, by definition, must have infinitely many solutions.
That's exactly right.
And just a quick question, not sure if it's important. What if the second row is 0, 0, 0, 0? Would that still imply the same thing?
It would also imply the same thing.
Okay.
Though, once again, I haven't exactly told you what echelon form is, but it's coming. It's coming. But before it happens, any questions about this? Is it clear that systems can sometimes have infinitely many solutions? And in fact, the dimension of the solution space, we haven't even talked about dimensions yet, but this is a one-dimensional space of solutions because x3 can be anything. So you can set x3 to be any number on the real line. That's one whole dimension worth of solutions, and then x1 and x2 are forced right from that point on.
So out of curiosity, wouldn't this make like some sort of plane or something?
It would make a line.
A line. Yes,
Right.
that's what I meant. Okay.
Actually, because you've taken multivariable calculus, these are the equations for three planes.
Yeah.
These three planes intersect in a line, is what this is saying. And in
Okay,
fact,
that's
this is like basically a parameterization for the line. Well, not a parameterization, sorry. A system of equations that gives you the line.
Yeah. Very interesting. It's actually really cool.
Okay. Let's do one more. 2x1 plus x2 plus 3x3 equals 1. x1 minus x2 equals 1. And then x1 plus x2 plus 2x3 is equal to 1. All right, go for it.
Awesome. So first, we're definitely going to make an augmented matrix.
Always the move, yes.
Always.
Always the move. All right, 1, 3, 1. 1, negative 1, 0, 1. Okay. And then 1, 1, 2, 1.
Yeah.
Perfect. Go for it.
So can't we just make the 1 in the second row a 0 by subtracting by half of R1?
Yeah.
Okay, perfect.
You're a brave man. I mean, I just warned you about those fractions, but he's going for it. That's okay. Let's do it. So,
is there another way to do it?
You could swap and then subtract 2 times row 1 from row 2, for example.
Oh yeah. I see.
So that would be my like coward's way.
Yeah.
You know.
Yeah.
But I mean, you do you. It's good.
Okay.
1, and we are subtracting row 1 over 2 from row 2.
Yes.
Okay, go for it.
So it would be 1 minus 2 over 2, which is 0.
Mm-hmm.
It would be negative 1 minus 1/2,
Mm-hmm.
which is negative 3/2. Yeah.
Good,
and then
good,
it
good.
would be 0 minus 3/2, which is also negative 3/2.
Mm-hmm.
And then it would be 1 minus 1, so 1/2.
Okay, very good.
You're right. You definitely got to be careful.
Yeah, for sure. And who knows? We may have already made a mistake, but we'll see
Yeah.
what happens. We'll see what happens.
So I also want to get rid of that 1 in row 3,
Oh, he's
or
not-
actually both of those ones in row 3, which we'll have to do in 2 different steps, I'm assuming.
Okay. How are you gonna do it?
Well, the first one, I'm thinking of the first index of row 3. We could also subtract by half of R1.
My goodness.
Definitely got to be careful.
Yeah.
We're getting it very
I'll check it with a
difficult.
computer at the end. But
Sounds good.
but continue. So 2,
So
1,
the-
3, 1, 0, negative 3/2, negative 3/2, 1/2. Very good.
Yeah, so then it's going to be 1, it's going to be 0.
Right.
It's going to be 1 minus 1/2, which is 1/2.
Very good.
Then it's going to be 2 minus 3/2, which is 1/2.
Very good.
A lot of fractions in this one.
Mm-hmm.
And then 1 minus 1/2.
Okay.
Okay, this is getting a little... Okay, let's see here. So now I want to make this 1/2 in row 3, the second index, a 0. So that we get our nice staircase.
Okay.
That's correct, right?
Yeah. I mean, your maneuvers are very gutsy. Let's see. Go for it.
It's getting dangerous.
Yeah.
So my question is, can we multiply row 3 by 2.
Ah, I'm so happy you said that.
Yeah.
You can multiply row 2 and row 3 by 2. Just get rid of it.
Okay, yeah, let's do that.
Yeah.
Because yeah, this
Actually, here's a recommendation. You can multiply row 2 by 2/3. That way you'll have ones. So
oh yeah, okay.
2, 1, 3.
Yep.
1, 0. Actually, I multiply by negative 2/3.
Yeah,
it's
yeah.
1,
So it's
1, and then I guess negative 1/3, right?
Negative 1/3.
And then 0, 1, 1, 1, 1.
Yeah, that's a significantly more aesthetic matrix.
Okay.
Okay. So now, oh, we can just multiply. I mean, not multiply. We can do row 3 minus row 1, because the second index of row 1. If
Wait. Row 3 minus row 1.
No.
You're bringing the 2 down if you do row 1, right?
Yeah. Oh, I see.
You're close though. You're close though.
Yeah, because if we do that, then the 2 goes into 0 we just made.
Mm-hmm. Reversing progress.
Yeah. Oh, we can just subtract the second row from row 3.
Very good, very good.
Yeah.
Okay, let's do that. So row 2 out. So now we have 2, 1, 3.
Exactly.
1, right?
Mm-hmm.
0, 1, 1.
Yep, and then it would be 0, 0, 0.
Mm-hmm.
Oh, and then it will be 1 minus negative, so 4/3.
4/3. What
So
does that? Yeah, what does that last equation say now?
Yeah, that's an interesting equation. Well, it's just saying 0 equals 4/3.
Which means.
Yeah, that's not good.
So what does that mean about the original system?
That it doesn't work.
And there's no solutions.
Yeah, no
right?
solution.
These would be, for example, in R3, these would be 3 planes that have no common intersection at all.
Yeah. Okay. Yeah.
So this here,
visualization.
no solution.
Okay. Okay, so I see. Now we've gone through the like 3 general.
Yes, we have in fact covered all the possibilities that you are ever going to see.
Yeah, the no solution and infinitely many.
And I will leave you with, because I've been hinting at it for so long, a formal discussion of what echelon form and reduced echelon form is, and that'll be it for today.
I'm excited.
And you now have basically a complete working theory of what anything can happen that can happen with a system of linear equations.
Yeah, I'm really excited. I'm gonna mess around with graphing these later tonight.
So what is echelon form? Let's see. Echelon form is the following. You have a matrix, okay? You have this staircase shape, okay?
Mm-hmm.
Let me draw it like that. Okay. Under the stairs, all zeros. There's nothing but zeros under the steps, okay?
Mm-hmm.
Make sense?
Yeah.
Nothing but zeros under the steps. Okay. In each pivot position, so like a pivot of the staircase, is a number that is not 0. So in here. So these numbers here that I'm coloring with like these solid blocks.
Yeah.
These are not 0. Okay?
Yeah.
The height of every step is 1. Okay?
Mm-hmm.
So none of this. Like no none of this. Bad. Not an echelon form. Okay?
Yeah.
The height of every step is 1. The width of every step can be bigger.
Oh, okay.
Okay? Not worried about that. Okay. Also, up here could be a mess. Any numbers may lay above the stairs.
Awesome.
Such a matrix is said to be in echelon form.
Mm-hmm.
Does that make sense?
Yeah.
Let me do a quick quiz. So, for example, let's see here.
this matrix is an echelon form.
Yeah, because the pivots would be, well, definitely the second zero, well, all of the zeros in the third row, and the zero in the second row, and then all of the numbers above those zeros are non-zero.
Right. So what are the pivotal? So by the way, this 1 and this 3 are the pivots.
Okay. Yes.
And if this was coming from a system of equations like this, right? This would be a system of equations that had 3 equations in 2 variables, right? And it would have it would have only one solution, because every column on the equation side has a pivot.
Yeah.
Make sense?
Mm-hmm.
Okay. And there was one redundant equation that turned into turned into zeros. If there is a pivot in every column on the equation side, then you have a unique solution.
Yeah.
Okay. So this, for example, like 1, 2, 0. This is not in echelon form, because I said there's a step of height 2 here.
Yeah.
Okay, perfect.
Yeah. That was a nice little visual, though. Yeah.
All right, excellent. What is reduced echelon form? This is what the computer does.
Yeah.
It just does those
we wanna
extra
make
steps. Yeah.
all of those pivots 1.
Very good. The first requirement is all those pivots must be now 1. Okay.
And that's so that you're working with like the most fundamental equation. System of equation. Okay.
Each pivot must be a 1. Also, above and below the 1s are zeros. So under the staircase is all zeros as before, right? But now also above the pivots, you have zeros as well.
That makes sense, because then that corresponding variable you can instantly solve for.
Okay, exactly. So now you know what echelon form is and what reduced echelon form is. Okay.
Yeah, I'm feeling pretty good.
A few things. If someone asks you, does the system have a solution? Does it have infinitely many solutions, or it has no solutions? You can read that off right from the echelon form.
Yeah.
If you actually, oh, sorry, go ahead, I didn't mean to interrupt.
Oh, I was just gonna say, you know, it has no solution if you have some, for lack of a better explanation, absurdity in the matrix, where you have, say, a row of all zeros that equals a non-zero number.
By the way, that's the only absurdity. You are guaranteed to hit it if there are no solutions.
Okay.
Right. So in your process of going for echelon form, you will see that absurdity at some point if there are no solutions.
And then for infinitely many solutions, you have like a free variable. Or so.
Exactly.
Okay, yeah.
On the left side of the bar, you will notice there's a column without a pivot. Okay?
Yeah.
Okay. And so you will go to echelon form. It's just a quick way to decide what situation you're in. Reduced echelon form is a great way to actually write out the answers. Okay?
Yeah.
Now, there's a little bit more work to do in terms of like formatting the answer when you have infinitely many solutions. Okay?
Yeah.
We'll work on that. There's really no formatting to do when there's only one solution. You just write it out.
Okay.
And there's also no formatting work to do when there are no solutions. You just say no solutions and you are done.
Awesome.
All right. Anyways, that was it.
Thanks so much for all of the help. I really appreciate it.
Of course. All right.
A lot of fun.
I'm gonna stop the recording.
All right, I hope you guys enjoyed that. For next time, we will review row reduction, everything we talked about. We'll probably try to be a little more systematic in terms of explaining, the different types of echelon forms and how they lead to like different styles of solutions. And we're also going to talk about independence and possibly spanning. So I hope to see you then. Peace.